Good afternoon, everybody. First of all, very sorry for the inconveniences that happened. So, without any delay, we'll start the session. Harshit, are you here? You can take over the session,
Yes, yes,
Harshit.
yes.
Yeah,
Yes. Good
thank
afternoon,
you.
guys. Good afternoon, everyone. So, are we waiting for the others to join, or we are starting the session? Anusha?
You can start, Harshit. I think all are here. I think only one person is not here. At least all are here. You can start.
Okay, fine. That's nice. Uh, yeah. We'll directly jump into the hands-on. Uh, Anusha, can you change me to the host? Like it's not leaving to share my
Yes,
screen.
I'm doing that. One second.
I hope my screen is visible.
Yes, Harshit.
Okay, fine. So we have had enough classes for theory, and it's time for practical hands-on session, I guess. So we'll deep dive into the script. So yeah, okay. First, I'll try to explain the script, then we'll run through the script, right? To give a backdrop of this, the script that we are, I mean, the data set that we are referring to is the rice diversity data set, which is publicly available. Okay, and yeah, these are the first. We have few set of packages that needs to be installed. So if you see my screen, yes, these are the packages that we are installing. There are, and again, all these packages are based on different versions. If you are using Biosim Manager, it's 1.18 and above, and your R must be 4.0.0 and above, right? For these packages. Then, yeah, we are running through the library, and then comes setting up the working directory. And here, uh, yeah. So, as we all know, there are specific files that we work with, right? The PET files, FAM files, and map files. So, for what we do first is like we try to prepare. This is in the data preparation part, right? So we are trying to read all these three files and convert them into a matrix, because in our matrix can easily integrate with the packages and tools, right? So what we do is we'll convert the FAM, map, and PET files into a matrix, right? And for the phenotypic data of this data set, we have in the database we have it. I'll share you I have shared you this, right? Here we have phenotypic data also. This is the phenotypic data file. So yes, so we are accessing that through R and running it as a table, and then we are trying to take we are trying to reduce the dimensionality, and we are trying to use it. Okay, and here this is a for loop for running all the files in the genome that has been defined earlier, and then we are trying to create the matrix with individual files. Yeah, once the we try to identify the SNPs, SNP DJ, GDS creation. This will actually create your SNPs with their IDs, right? So post that, we'll create two files. That is, for our analysis, we need the genotypic features and the phenotypic features, right? So for that, we are trying to create two data frames. First one will be for genotypic traits, and second one will be for phenotypic traits. So in the GWAS section, then we'll run the GWAS analysis. And after running, what we do is we try to add. So in the chromosomes, we have so these files contain continuous chromosomes, right? So we have to create a correlation matrix for that. Correlation matrix, which actually separates each chromosome. So if you see here, this is actually the first chromosome in the whole matrix. These entities belongs to first chromosome. So we try to make them into respective chromosomes. We try to correlate them into respective chromosomes, right? Then we try to check this is basically a MEF function. This estimates the effective tests for those particular chromosomes. And if you see here, yes, here. So this we in this, if you head the particular data that we have, you have various phenotypes. As discussed on the other day, I think it would be better if I show you. You could understand it much better. Fine. If you try to visualize the data, how it is going to be, it's going to be the ID, that is NFST VID, followed by the name and the chromosome position, followed by the phenotypes, right? You get different phenotypes. In this data set, if you hit the data set, you can see different traits in that. So we are selecting one trait out of it, that is plant height, right? For that, we are processing the whole process. Fine. So after creating the correlation matrix, we are trying to identify the tests, and we are performing the summation to identify independent tests. And then we'll try to filter the list of SNPs. After filtering the SNPs, we get our new, this is basically filtering. After filtering the SNPs, we get the new file, the filtered file. That thing we are going to generate the Manhattan plot. And in Manhattan plot, you can change your threshold, right? For this data set, set 3 as a threshold, the log p fold change value. Because if you look at the data set, there are outliers from 3, right? So you can change it. You can change it for 4 also. That depends on the exact data set or the study that you're working on. So yeah, uh, yeah, that's the code. Fine. Let me try to like run the code, uh, and we'll see. I don't know if I get any errors. R is always like you have to close, open, do stuff to get things. Let me try. So yeah, this RM remove list, whatever is that, this code is actually very helpful. Like when we are working with the R environments, so if you are doing different analysis, your whatever analysis you have done previously will be in your global environment, right? This code actually removes your environment and makes it clear for a fresh start, right? So yes. Let me set my working directory. So this is my current working directory that I'm in. Let me run it.
Harshit, just
Sure.
for sorry for the interruption.
Yes,
Just
sir.
check it out if anybody is then in the waiting room.
Yeah, I'll check. I'll check that.
Yeah.
I think I've admitted all. Yeah. Yeah. So yeah, talking about the data set. So what I did was like I downloaded the data set from the rice diversity data set which I told. From that, what you need is your all the GWAS files that is required, and also your what I could say the GDS file or the phenotypes file and genotypes file basically. So that I got from the data set. So from there, I'm trying to access it. I've downloaded locally and I'm working on that directory right now. Okay. So this is this I have access directly to the link. And if you see, like, this is the first 15, 1 to 5, the first five I've given to head. And if you see here, so this is the ID, and these are the phenotypes. Let's say flowering time at Arknas and flowering time at Faridpur. This is related to that particular study, right? So that particular study has these phenotypes in that. Okay? This is considering basically all the files, the map, the like, and also I'm trying to remove the null values, right? Again, it will be problematic for you have null values. So yeah, so after doing each dimension reduction, you are getting the values here, like how many traits and how many numbers it has been reduced. So the number of observations or values it has been there. And yeah, this huh, yeah. So now you actually have the S&P summary here. Okay. So this generates the S&P summary wherein you have total number of samples. That is, we have processed these many samples and we have identified 33,707 SNPs. Okay. And their sample X SNP. That's how they're stored. Okay. Yeah. Now we have to prepare our what genotypes file and the phenotypes file. So for that, we have this file and we are reducing the dimensions. it's taking time. So here we are trying to convert the data into a correlative matrix, which has we are classifying it into different chromosomes according to the position, right? From 1 to 5,888 is that first chromosome. So we are trying to divide the thing into different chromosomes. So yeah, this is basically like, in this region we don't have data from pertaining to that location. So it's showing that the last one, the 12th one basically. It's taking a lot of time. Um, okay, fine. So we'll discuss about the MEF. Okay, so what we are doing here is first we are trying to create a correlation matrix, right? After that, we are trying to calculate the effective number of tests. If you see the MEF or effective number of test analysis is most commonly done in GWAS studies. So basically, what it does is it is correlation between the SNPs, different SNPs, for its association with the uh, what I could say. equilibrium, right? So how it is correlated and how it is different, or how it is a variant, how it is a SNP. That's what we analyze in MEF. And if we have to like so after doing the MEF analysis, we try to check the number of independent tests also. That's because like all the markers are like might be, most of them might be independent due to correlation, right? Uh, so yeah, so like we were talking about the correlation, right? So these numbers are independent, like independent because all the markers can be independent. Uh, so what is the interface? Like what do we infer from this? This is basically like when you perform this, you know that there is often like less number of markers that are actually having an effect on this, to identify those markers which are actually the significant SNPs. We are doing MEF tests, right? And yeah, this ran, right? Let me run one more. If the markers is highly correlated, let's say, so then testing them as independent would inflate false positives, right? I'm talking about the error rates of our testing, right? Type 1 is our false positives, and type 2 is our false negatives. Yeah. So we are trying to reduce our error rate basically by doing this process. This is the part where we are actually trying to analyze the association in GWAS. Like GWAS is like genome-wide association, right? This is where we are trying to understand the association of one chromosome with the other, right? Hope this is done. So, four. Okay, it's running. So yeah, here, here we are trying to sum the MEF of each chromosome from the correlated matrix, whatever we have identified, the effective tests, whatever we've got, we are going to sum that. And from that, we are going to like understand the independent tests. Basically, we are trying to add the effective tests and identify. It is going to contribute to reducing the false positive rate for RSTP. And you can, it gives us an edge to set the threshold for consideration. Yeah. So the last one, yeah. Why is it showing error here? Is because like the matrix contain negative eigenvalues because of the data, right? But that doesn't actually matter. Like you are here for the test, you are actually the metric for the test is basically the eigenvalues. So it is negative is what it is telling. That's a minor error. That's just a warning message. We can ignore that. And for the 12th one, that is basically we don't have this region in this data set for the 12th chromosome. So that's why it's showing. Uh, so we set the threshold and we are trying to filter out the list of top 1%, right? And we are setting the threshold. I mean, we are getting the list of top SNPs, and also we are trying to set the threshold to like log p values to uh, minus 10 power minus 4. That's what we are setting. So this is the list and values that we are getting, and we can visualize this as well. Yeah. So yes. So for this data set, observing on the data set, I could come to a conclusion that log 3 could be, I mean, value of 10 power minus 3 would be a better threshold. So these points which are there, those are your outliers, and this is the threshold. So yes, Manhattan plot. Things worked. Cool. Okay, guys. Like I, I think you got, you understood like what we are trying to do and how we are trying to get things done. Uh, I'm now open for any kind of questions or like, yeah, if you have. Sir, hello.
Yes, Harshit?
Do you want to add anything, sir? Like for this, you wanna?
No, no, you can continue.
Uh, no,
No,
like, do you wanna explain anything here? I think the
no,
code
no,
work we are.
no.
Uh, so to give you a preview, guys, this is the actual R script that we use for processing real data. So you have certain things that we have included here, like let's say few things are extra as well. So you can try out running PCF plots for this, and you can do other. You can add or delete some parts of the code. Uh, let's say this remove list is just my thing, like that's for convenience and it's not required in the code. So this is what we use for running the GWAS pipelines. So yeah, I'm open for discussion. Like I think I can't see the chats if I'm presenting.
Harshit, there are some questions in the chat.
Can you please read it out for me? Like I should
Yeah, yeah.
exit site. Shall I stop share and answer those? Will that be fine or?
I will read out the questions for
Yeah,
you.
yeah, sure, sure, sure.
So, from Savita, they've asked that can you briefly elaborate the steps involved in GWAS? And
Okay.
can you repeat this result analysis, sir?
Okay, okay, fine.
Yeah.
So first, we'll understand the brief about the GWAS, right? So first, what you are doing as a steps, I'm telling you. First, you will try to run the packages, install the packages, then load the packages through library command. Then we have our setting the working directory, path, and other stuff. And then you have these GWAS files, the raw files. So for that, whatever ped or fam map files, whichever is there, these files we are going to process for our analysis into matrix, right? So basically, why we are converting them into matrix? Again, R is basically used for two main reasons, right? One is for statistical analysis. R is very good for statistical analysis, and R is also good for visualization, right? How does this R help for statistical analysis? Is through matrix, right? So this is like so we are trying to convert whatever the analysis or whatever data, uh, anything that we get, we try to convert them into matrix, and through matrix, R is able to perform any kind of statistical analysis that is required, right? So what we are doing is we are converting these files into our metric files, and then we are trying to get this is the genotype files, right? And then comes the phenotype files, phenotypic data, right? That this the present data, this part is the data preparation, right? First one is installations and libraries, and the second part will be our data preparation. Data preparation is wherein you will process the genotypic data and the phenotypic data. Phenotypic data we are taking from their that data set, so which contains different phenotypic data like the uh, let me try to get that. Okay. So this is the phenotypic data of the data that we are processing. So here, this is the ID, and these are the phenotypes, right? Leaf pubescence, flag leaf length, and like time of flowering time at Arknas and stuff like that. So here we took the plant height. Where is the plant height? Pinnacle length, seed length, right? These are phenotypes. So this has good documentation of all the phenotypes that they have observed, right? Out of this, we have taken plant height for our consideration, right? Okay, I'll try to close this, but this is not really need to close. Okay. Okay. So after our data preparation, what we do is we go for we have to prepare the pheno data also. We have to convert it into matrix. So after that, I'm trying to loop it, right? Loop all these three files or three converted data frames or matrices that is there into to process for processing and storing it on our global, uh, I mean, in the R ecosystem. So yeah, so this part of code basically does is like it will take all the files, it will reduce a dimension, and it will store in our it will store as a new matrix or data frame, right? Then comes your SNP creation, right? In SNPs, what we are going to do, we are so after creating the phenotypic data and genotypic data, we need to handle the missing values, right? So all the missing values I've used, omit I've used for missing values. Then, yeah. So now coming back to the, let's say, this package that we are using, SNP Relate. So SNP Relate package needs the files in a particular format, that is our GDS format, right? So we are trying to like convert the data into GDS format for the analysis, right? So this SNP GDS creation genome, that is actually creating your GDS file, right? Then comes our GWAS analysis, wherein like you start with our genotypic file, genotypes file data frame, and then you have phenotypes file data frame. So in that you can I was on the wrong side. Okay. So after reducing the dimensionality of these both, if you see here, I've selected plant height, right? Uh, so after creating both our genotypes file and phenotypes file for GWAS analysis, we can perform GWAS. So this is running your GWAS, right? So you give your phenotypic file info and genotypic file info and parameters you set, and then like you create the new file. So now we have GWAS as a file created when if you run this. Out of the file that has been created, you need to now understand, you need to give it data regarding the chromosomes, right? So what do you do for after getting these analysis files? We need to understand the effective number of tests, what I told. We need to first, in as part of that analysis, what we are trying to do, we are trying to convert that, we are trying to create a correlation matrix and feed data of our chromosomes, right? The like we are going to divide the whole data into chromosome level. So basically you will give from which position to which position is your first chromosome, which then second chromosome, third chromosome, fourth chromosome, and so on. So that we'll do, and we'll try to next we'll find the independent test and how it is dependent, right? So after getting that, we can set the threshold, right? So where is it? Yeah. So we can set the threshold, and then we'll try to get our filter. We'll get to filter the new file that is being created with our filter for SNPs to identify the SNPs. And in the analysis part, in the visualization part, we are trying to set the threshold as like based on the data, we can vary the threshold. That is like you can change the threshold that you want to set, and you will try to generate the plot, right? Uh, yeah, so in the Manhattan plot, you are giving the file which contains our filtered SNP data with the chromosome value we have given, and then we have given SNP parameters. Then we are giving the color, and then we are giving the threshold. This is the line, and log P we are going to analyze, and that we are getting the plot. So yeah, I think okay, fine. If I have to give a quick snippet of what we are doing, so first you will do setup and library preparation, then comes data preparation, then comes your missing data handling, and then comes your GDS file creation for our packages that we are using. Then we do GWAS analysis, followed by the effective test and independent testing, and then we'll go for threshold setting and visualization. Right. I think in terms of steps, that uh, looks good. I hope that was a walkthrough to what we have done.
And Harshit, there's a question: how to get the raw data? From where to get the raw data?
Uh, so actually, like to if you are not working on, let's say, real data, if you're not generating the data through sequencing and stuff like that, it will be tough for you to get raw data because there is less amount of open source GWAS data that is available. If you're getting through, like if you're working really on the process, you will get it more easily. And getting raw data is, yes, in GWAS it is a bit tough to get the raw data.
Yeah, Harshit.
Yes, sir.
Yeah, just I wanted to speak out here is that even yesterday I had taken up this question. I told that you can get the data from the HAP map and other sources are from the research papers. That
Research
even
papers
we
we
had
can, yeah, true, true,
yes, yes.
true.
So that
Hap
is
map,
these are the HAP
yes.
map and there is one more database that is the Geno 3D. No,
Huh,
yeah, these are the some of the things, but above all, the data will be less there. So that is the thing. The data which we are using or which have used are from the certain research papers.
yes, yes,
So that you have to keep in mind that exactly what data you are looking for. So Jeewas, this is one thing that as Harshit told, if you have some wet lab researchers with you, it is easy to get the data. Okay, Harshit, please continue.
yes, sir. Yes, yes. So there are two sources basically. One through your own analysis, and one through public repos and literature reviews and publicly available data basically. So you can find it in Jiva studies. They would have their own Git repositories wherein they have these databases. I mean these data stored. Can you go to
Hello,
the
sir.
next question?
Hello. Am I audible?
Yes.
Yeah, I just wanted to ask, what is the structure of GDS format file?
GDS format file.
Yeah, how does it, if we visualize the raw file and when after the creation, like you showed up the step. So, what will be the exact content? Only the genotypes, or it will also contain the phenotypic, the data from the phenotypic file?
No, it is basically no. When you're creating your GDS file,
Okay.
what you do is like you've already you're taking into consideration your phenotypics and genotypics, right? So when you try to create your GDS file, you will have information regarding the samples, the number of SNPs, and the related informations.
Okay. So can we have like multiple traits in that GDS file, or it is only focusing on single trait?
You can have multiple traits.
It can have multiple traits.
So can you see this? Can you see this? Uh,
Yes.
yeah, this is the structure of your GDS file.
Okay.
Yeah.
Yeah.
Okay.
Okay.
Next question. How to install these packages? Kindly show me, sir. Okay. So yeah, there are two repositories for packages, right? For R, one is CRAN, which is like the sole repository of our core team, which constantly gives you updates, and that's a repository for packages through CRAN you can install. So some of the steps to install packages would be like in your RStudio, if you go to packages here you have install, and if you give install here, if you specify the package name, you can install it right here. Let's say some Plink QC, right? So I give install. Oh, it is asking me to end the session. I can't do that. Okay, so that's one of the ways, and the other way is through the command, right? You have install.packages. Within the bracket, you can name the package name within the quotes so that it can pick the package from there. The other repository, the most important repository for bioinformatics, is your bioconductor. So bioconductor is a open source bioinformatics project developed by bioinformaticians for all the uh, bioinformatics related packages. It has R packages, it has Python packages. It is predominantly dominated by R packages specific for bioinformatics. So from there you can install. So the issue might arise when we use you can install from bioconductor, you can install through your desktop, or what you can do is there is one more package called BioC Manager, right? This is a wrapper, or let's say it's a API tool kind of thing, which brings your all bioconductor packages into R, right? This manages all the bioconductor packages. So if you have installed BioC Manager, you can install BioC Manager. Then if you install BioC Manager through BioC Manager, by giving this command, you can install the bioconductor packages through BioC Manager, right? So a bioconductor is a repository, and BioC Manager is a installation tool that is available within the R ecosystem. Through BioC Manager install, we can install bioconductor packages right away from your like RStudio, right? This is a bioconductor package, and these are normal CRAN packages, right? I think I answered that question. Okay, once you install the packages, you can load the packages by library and you can give the name of the package. Please send us the R script and input data for practice or try out ourselves. Yeah, sure. We'll send that. We'll send the script. Okay. Can you repeat this analysis? Where can I get the raw data from? Yeah, raw data. Yeah, as we mentioned, it is really hard to find raw data because there is no as such like you have a dedicated GWAS repository or dedicated GWAS database for getting all this. So it's tough to get in public. So one of the ways that you can do is one, you can check the literature review and find out the packages. The other way is through your own wet lab aspects. Like you can find out few people who are working on GWAS studies. From them, you can get the data.
Hello.
So, yeah. Hello.
So can you please explain that MEF test again? Only the test, not the code part. Like actually, I wanted to know the significance of that test.
Okay, fine. So now, see, the whole idea of doing MEF test is to identify the correlation and the significance, right? There are two parts. One is the correlation between the chromosomes, right? With let's say, what is the SNPs in chromosome 1 with chromosome 2 with chromosome 3 with chromosome 4. So this is where you try to analyze whole genome or whole all the chromosomes and its variation at once. That's what you do in your MEF test, right? And then you perform independent analysis, independent tests. That is to identify the significance and to understand, to reduce the false positives or type 1 error, right? So you try to reduce your errors by independent testing. what you do is through you correlate and you test the whole thing. Then you try to analyze each individual chromosome, and then you come to a conclusion of how the actual data is. I mean, how your what I can say, how your samples are, right? So once you are done with that, then you can go for uh, proper threshold calculations, and then you can visualize your data. Uh, did you get it? Like,
Yes, sir.
yeah.
Thank you. So can we use this test in the diversity analysis?
Diversity analysis, as in you're talking about
Uh,
the gut
actually,
profile.
yeah, actually, I work in a lab where we use marker technology. It's an agricultural company, so we
Oh,
do diversity analysis of based on Jacquard's distance.
okay.
Okay, so like you told that this the MEF test can be used to identify the significance of the markers and how well those markers or how well those markers performs around the chromosomes. So
Yeah,
like, can we use this test in diversity also?
you can try that out. I'm not sure, but for diversity, we have other indexes, right? We have Shannon index, we have betweenness, and
Yeah.
those other indexes are there, right? Simpson, Shannon index, and all. So see, again, I'll tell you. So when what happens is you can use different things in different. You can apply it for different techniques if you know the process. But the thing is, there are these standards, right? Every
Mhm.
every what I could say, every analysis or every kind of analysis has its own index or units to measure, right? So for diversity, we have other indexes than MEF, to be specific. For in GWAS, we are using MEF. So if you ask me the what is the difference between these two, they're doing the same thing, but the indexes are different. Like if your company or if it is fine with working with different index, you can go with it.
Okay. Okay. So it will also work for big data. As if like here I can see the file is of 44K. So like it will work for big data also within a very short time period. Like
44K is just the name. Okay, it's
I
around
thought.
129, 121 MB, 100 MB, 50 MB, like that. Yeah,
Okay. Okay.
it will work. It will work. It will work, but it'll take hell lot of time.
Yeah.
I mean,
Exactly.
like, to process it's really hard.
Yeah. Okay.
Yeah,
Thank you.
thank you. Any other questions?
No, Harshit. You can continue.
Uh, yeah, like I'm I'm actually uh, done, I guess. Like, if you have questions, I'm open to answer. Or if it's not there, I think we'll share the script. You can try your hands-on, but make sure you actually get correct proper versions of R and R Studio and your packages, right? If you're working with BIOC Manager, again, BIOC Manager has its own versions. So make sure your versions are right and then try. The problem with R is it's very good in getting statistical and visualization, but at the same time, the issue with R is to work with these dependencies and the version control. That is really tough. Like, if one thing of the multiple parameters that are there is not working, your code will not run. You will not Your package will not get properly fixed. You can't call functions while processing your data. So make sure all your packages, versions, everything is proper, and then try to run. It should run. I have fixed the bugs so many times, so it should run. So yeah. Anything else, sir? Sir, can we?
Yeah, we can. I think Anusha, can you just share the feedback? And I will just request everybody to kindly on their videos so that we can take a quick snap and we can close it. So, Harshit, if you please unshare your screen, and we request everybody to switch on their videos. We'll take a snap for all. Harshit, I think you have to.
Yeah, 1 minute. I'll do that.
Other participants, if you can just switch on your videos. Other participants. Participants, please on your videos. Participants, you can on your videos. Okay, I think, okay, fine. If nobody is switching on, okay, no problem. Anusha, you can give the closing remarks.
Yes, sir.
Hello?
As we have come to an end of 3 days workshop, I would like to thank our speakers, Dr. Prenan Bakchi sir and Mr. Harshit, for sharing their expertise and knowledge. And I also thank everybody for your active participation. We hope that you found this workshop very informative and valuable. So we will be sharing our feedback form. I request you all to please fill in the feedback form as it is very important for us. I would like to conclude with a small announcement of the upcoming workshops. We have an upcoming 1 day free workshop on cloud computing, which is scheduled on 3rd of August between 7 to 8 p.m. IST. And we're also organizing 1 week online hands-on workshop on advanced deep learning using Python in collaboration with Biopractify, Delhi. This is scheduled from 5th to 9th of August. Those interested can register themselves. So the details regarding the same will be shared in our announcements group. Also, we have an upcoming 4th International Conference on Bioinformatics and Data Science. The abstract submission dates is extended to 1 more week from tomorrow. For more details on the guidelines and the registration fees, please visit our official website. Thanks again for joining us today. Stay updated across all our social media official pages for our upcoming workshops and training programs. Once again, thank you so much. We will be ending the session now. Thank you. And the certificates will be emailed to your all.
Anusha just mentioned that in the feedback form, please mention your name properly. The same name will be put in the certificate.
Yes, sir. Yes, sir. It is mentioned in the feedback form as well. Okay, sir. We will end it.
Yeah, Harshit, you are the host. You can end the
Yeah.
meeting.
Yes. Thanks, guys. Thanks for joining this evening. I hope it was informative and interactive. Thank you. Thank you all.
Thank you, Harshit.